Hi, it's Ryan. We're going to continue our historical perspective, jumping back into the 16th and very early 17th century with a man named Tycho Brahe. Tycho Brahe. So I don't know if that's actually how you're supposed to pronounce it, but that's what I was told once. Tycho was alive from 1546 to 1601. He died a little bit younger than expected. He was a Danish nobleman, and he was most famous for being just that, a rich nobleman. But he was an astronomer, and I guess technically a writer, though his book was mostly pictures. And a teacher of sorts. Anyone that would listen, Tycho loved to talk, so. Tycho had abnormally good eyes. Tycho had incredible eyes. An example of how good his eyes were, he could look at the moon closing one eye, and then keeping his head where it was, open the eye and close his other eye, and from the small angular displacement he would perceive that the moon does, he could estimate a very accurate distance from the Earth to the moon, just using his eyes. He did the same thing with a couple different comets that passed by in his lifetime. That phenomenon he was using is known as parallax, and it's very similar to what we perceive as retrograde motion, it turns out. But anyway, he had incredible eyes. And with those incredible eyes and many of his nights, he would often drink a lot, and while he was drinking, he would observe the night sky. And in doing so, he decided he would start to create these maps of the night sky. So Tycho created thousands of incredible sky maps. Turns out Tycho was a nobleman and got very drunk often, and he was known to be a little argumentative. He's also known to not have a nose. He lost his nose in a duel with his third cousin after a night of drinking and arguing. He challenged his cousin to a duel, and they went out and had a sword fight in the dark. And during that sword fight, Tycho lost most of his nose. So he was known for having a big metal nose that he would stick onto his face. It turns out Tycho would go to a lot of parties, and near the end of his life, he was at a party, and the guest of honor were running late. Back then, it was impolite for you to leave the room before the guests of honor arrived. Well, he really had to relieve himself in the bathroom, but in order to maintain his high standing, he decided to stick around until the guests of honor arrived. Eventually, they did arrive, but it wasn't in time before Tycho contracted a pretty bad bladder infection from holding his urine too long, and later that week he died. For hundreds of years, it was argued that Tycho did not actually die from an infection, but was murdered. It was suggested by mercury poisoning, but we actually exhumed his remains in the late 20th century and determined that it was not murder and that he died of probably the bladder infection after all. Anyway, Tycho was a proponent of heliocentricity. He thought that a geocentric universe was outdated, and he thought the sun must be in the center. And he started teaching that. But when the church caught wind that he was teaching heliocentric universe to people, they came by his fairly nice mansion, knocked on the door, and they said, "Tycho, we heard you're teaching heliocentricity. You know that's not how it works, right?" And Tycho said, "No, I think it is how it works. I know we can't prove it mathematically yet, but I think it is how it works." And they said, "No, you don't, Tycho." And Tycho said, "Yes, I do." And the church said, "Do you remember Bruno?" And Tycho said, "Oh, you know what? You're right. It is geocentric." And with that, Tycho created his own cosmology. And in Tycho's cosmology, he put the Earth at the center, and then going around the Earth, he put the sun, and then going around the sun, he put all the other planets. So we've got Mercury, Venus, Mars, Jupiter, Saturn. So he put all the other wanderers orbiting the sun, and he said, well, if they're all orbiting the sun, that's okay, as long as the sun is orbiting Earth. And so that was how he got around the church burning him at the stake. And I've read that several other astronomers during this time would create models similar to this, where it was a heliocentric on top of a geocentric model. Another interesting, odd thing about Tycho is that he kept a house dwarf. It was just a little person that he kept and made this little person kind of wait on him and his guests during dinners, and the little person would eat under the table with Tycho. It was very strange. He was a very strange man. Anyway, that's Tycho in a nutshell. After Tycho's untimely death, his assistant, after a few very long court battles, ended up getting his sky maps and working with them. His assistant is a famous man named Johannes Kepler. Johannes Kepler. He was a mathematician and a very good one. Johannes had terrible vision, though. He had very bad eyes. And so one of the reasons he started working with Tycho was because of Tycho's extraordinary vision, especially at night. And he wanted to work with Tycho's sky maps. He was also under the belief that the universe must be heliocentric. And he wanted to use Kepler's wonderful sky maps to map out the motions of the wandering planets and figure out what their orbits around the sun must be. So Tycho, having not been very good at math, allowed Kepler to work with his sky maps. But once Kepler heard that Tycho had created a geocentric model, they started arguing. And in these arguments, Tycho ended up taking away his sky maps from Kepler. Eventually, they would work it out, and Kepler would get the sky maps back. But when Tycho passed away, Tycho's family went after Kepler to get the sky maps back, took him to court, and Kepler lost possession of the sky maps again. I heard a couple years later the family kind of gave in and said, I don't really know what to do with these sky maps. Why don't you take them? And Kepler ended up finally getting the maps. With those, Kepler created hundreds of different hypothesized orbital shapes for the planets. And his goal was to be able to predict many of the astronomical phenomena that we see, in particular, retrograde motion. Kepler ended up figuring it out. He figured out how the planets orbit around the sun. And he did so by discovering his 3 laws of planetary motion. So we're going to say Kepler's 3 laws of planetary motion. Many people wonder why Kepler didn't do more than just these 3 laws, but it turns out Kepler had a vivid imagination, and he had a bit of an eccentric mother. His mother was accused of being a witch, and so soon after his discovery of these planetary laws of motion, he was kind of forced to try to get his mother out of prison for years. His mother was accused of being a witch and locked up, and he had to work very hard against the courts to finally and eventually get her out. And I think she passed soon after getting out. Something that did not help his mother's case was that one fun day, Kepler woke up from having a vivid dream and wrote a book based on his dream about being on the moon. So he basically conceived of human space travel and wrote about it, and this didn't look so good for his mother's witch trials. Anyway, eventually he got his mother out, and he did create these laws of motion, but these are the thing he's most famous for. The first law of planetary motion is the law of ellipses, and it states that each planet orbits the sun in an elliptical path with the sun at one focus. Each planet orbits the sun in an elliptical path with the sun at one focus. I'm going to write out all of the laws, and then I'm going to give you explanations and interpretations of them, so kind of bear with me through this. And I guess we could say of the path parenthetically, just to be really clear. Number 2 is called the law of equal parts, equal time, or equal times, equal areas, Law of equal time, equal areas. And this law states that a line connecting a given planet to the sun will sweep out equal areas in equal times. A line connecting a planet to the sun, obviously these lines are imaginary, will sweep out equal areas in equal times. Number 3, his third law of planetary motion, is known as the law of harmonies. And the law of harmonies is best stated mathematically, it turns out, everyone's favorite. It's written T1 squared over R1 cubed equals T2 squared over R2 cubed. And so we'll say where T is defined as the orbital period, usually in years, and R is defined as the mean radius or distance from the star to the planet, and we'll say usually in AU. Recall, 1 AU is defined as 1 astronomical unit, and that's the average distance the Earth is from the sun. One AU is approximately 1.50 times 10 to the 11 meters. 149,597,870,700, I think. Anyway, that's 1 AU by definition. And that's the law of harmonies. What we'll really need are some explanations to help these make more sense to us. Some explanations. So to explain the first law, the law of ellipses, I think I'm going to draw a picture. So for our first law, the law of ellipses, we're going to use our imaginations, but I'll guide you through it. Imagine taking a big piece of cardboard, sticking it on the wall, and placing 2 tacks kind of right in the middle, like so. From those tacks, you would then hang a piece of string. And then imagine taking that string and pulling it taut so that it looks something like this. So you pull it taut with a pen or a marker, and then keeping your marker on the page and that cable taut, you can drag your marker, and the ensuing shape would give you an ellipse. And so what you would see happen is that you would see an elliptical shape occur, like so. So this is an ellipse. And that is a focus of the ellipse. That is a focus of the ellipse. Or if you wanted to say them together, they would be the foci. It's the plural for focus. Pretty sure ellipse has one L, by the way. So no, it has two. I was good. My brain today. Okay, so the thing to remember about the planets, most planets have nearly circular orbits, which we would say in math, low eccentricities. Low eccentricity. And so in general, the more circular an ellipse, the more or less eccentric it is, or the more oval an ellipse, the more eccentric it is, whereas a straight line would be the most eccentric you can get. Sounds a little strange. Anyway, you don't need to know that. You just need to remember that an ellipse is not a circle. It has two foci instead of one center. And we think the planets, even if they look nearly circular, are still traveling along ellipses. Number 2, the law of equal time, equal areas. So what I'm going to do here is I'm going to draw the sun. And the sun is at the focus of the elliptical path that the Earth takes around it. And so I'm going to go ahead and draw that elliptical path like so. And this is a sort of more elliptical than the Earth's orbit is in real life. In real life, the Earth's orbit would look almost circular. But for this exercise, we want to really see the elliptical shape. And so what we're going to do is imagine if the Earth were here, in about 1 month's time, it might make its way to here. So that change in position of the Earth will represent 1 month in time. If the Earth started over on this side of its orbit and traveled for 1 month, it may only make it that far. And so what the law of equal time, equal area is saying is if we connect the planet and the sun with a line, that line will sweep out some area. And the same can be said for when the planet is over here. That will sweep out some area. Now the idea is that these areas are related, A1 and A2, as long as we're timing the Earth's motion for the same amount of time. So we know due to this law that A1 must equal A2, even if they look a little different. So you might be wondering then what this tells us, but we'll see that in our interpretation. But you can kind of think In order for the Earth to move a longer distance than it does over here, it must be traveling at a different speed, right? In order to go a longer distance in the same amount of time, the Earth must be moving faster. Anyway, the third law, the law of harmonies, that scary mathematical statement, what this is really saying is that all of the planet's journeys around the sun are inextricably related. All of the planet's journeys around the sun are related. So those are some good explanations for his 3 laws of planetary motion. And finally, what I'd like to give you are interpretations of these laws. So back to the law of ellipses. What this is basically telling us is that there's an interaction between each planet and the sun. And even if that interaction seems different, it causes the same outcome. It causes an elliptical path. So I'm going to write that there is an interaction between each planet and the sun. Now keep in mind, this is before we discovered gravitation and gravitational forces. In fact, when being asked about what this interaction may be, Kepler was forced to admit that he had no idea. He said it's probably something like magnetism, but he had no idea. That's actually a very innovative thought, by the way. Number 2, the law of equal parts, equal times, or equal times, equal areas, or however you want to say it. The closer the planet is to the sun, the faster it travels. The closer a planet is to the sun, the faster it travels. And last but not least is the law of harmonies, and really you should test this one on your own. What you should do is look up the distance in AUs and the orbital period in years for a couple planets. For example, the Earth, the period for Earth is 1 year. That's easy. The orbital distance for Earth is 1 AU. And if we take the period squared divided by that distance cubed, we would get the same number that we should get if we do this for any planet, which is 1. So your mission to test this would be to look up potentially maybe the period for Mars and square it, and the period and the distance for Mars and square and cube it, and that should end up giving you 1. And you can test that for all of them, although I wonder if Pluto will cause an issue. But the actual interpretation for number 3, so what you should actually write for this interpretation is that the sun is in control. But you can always test it. It's kind of like magic. And it's amazing to then think that in the 17th century someone discovered this. So those are Kepler's 3 laws of motion, some interpretations, explanations, and definitions, as well as a little backstory. I hope you enjoyed.